In this video, we're going to continue our discussion of improper integrals. So just to recap real briefly, what do we know about integration, specifically finding the area under the curve? Well, the fundamental theorem of calculus will allow us to find the area, the exact area under a curve, if f of x fits or satisfies some conditions. One, the interval that you're integrating over has to be finite, right? It has to go from A to B on a closed finite interval, in fact. And second of all, your function has to be continuous on that interval. And so if these two things occur, you're on a closed finite interval and your function's continuous, then we can say that the integral from A to B of f of x dx will be the antiderivative evaluated at B minus the antiderivative of little f evaluated at A. So in this video, we're going to examine what happens if some of these things fail. Well, if they fail, then that's why we have integrals that are called improper. This is what an improper integral would be, is either if your interval was infinite, that's what we're going to talk about in this video, or if your function has like a vertical asymptote of some kind, which is what we're going to discuss in the next video. All right, so let's assume that our function is continuous, but it's defined on an infinite interval. Infinite means it goes either to infinity and or to negative infinity. All right, so if you had your function defined from A to infinity, for example, then how are we going to compute this integral here? Well, we can't use the fundamental theorem of calculus because this condition has been violated. This is not a finite interval. So what are we going to do? Well, we're actually going to implement a pretty slick idea, a pretty smart idea. What we're going to do is this. We're going to integrate from A, and then I'm going to make up a dummy endpoint, a fictitious endpoint. So let's say from A to B, right? So there's no B in this problem. I'm adding the B into this integral. Now, if B is finite, which it is, then we can compute that integral. So leave a little space. I'm going to add something in front of here in just a moment, but we're going to integrate from A, not all the way to infinity, but only up to B, which is well short of where I want to be. I actually want to continue on the rest of the way, but we'll get to that in a moment. So the integral from A to B of f of x dx, that's defined. You can do the fundamental theorem of calculus on that because the interval is finite and all those good things. A will be a number that you will be provided, like 2 to infinity or 5 to infinity. This lower limit will be like 2 or 5. Now B, because that's not a fixed value, no one gave us a specific B value, they gave us infinity, this is going to stay a letter. This is going to stay some constant, right? And so unfortunately, when we get our answer, when we do the fundamental theorem of calculus and we get an answer for this guy, it will have B's in it because it's sitting there waiting on us to on us to tell it what B actually is, right? But as soon as we get around to deciding what we want our endpoint to be, then we'll plug in B, and then we'll have our definite answer from 2 to 10 or 2 to 15 or 2 to 20 or 2 to 100 or whatever the case may be. Now here's the slick idea. We kind of got around kind of a backdoor way of being able to use the fundamental theorem of calculus. Now that this definite integral has been computed or can be computed, watch this, we're going to take the limit as B runs on its way the rest of the way to infinity, but that's after the integral's been done. So what happens is we'll go from A to a kind of a floating B value, if you will, so that we can use the fundamental theorem of calculus, and then we'll push that B all the way out to infinity, check out this limit, after the integration's been done. And so this winds up giving us the same thing as integrating from A all the way out to infinity, and kind of using the fundamental theorem of calculus in kind of a backdoor type of way. So it's a really, really smart idea. Now there are a couple of alternate things to consider. We're going to go through the last two very quickly. What if it was negative infinity up to a number rather than from A up to infinity? Just a very small change in notation is all. Here, b, the endpoint, is the fixed value. So we'll go from a to b, where a is kind of a floating mystery number, do the definite integral, and then we'll push a left to negative infinity once we're done. But it's basically the exact same idea as what we had before. Now, what would happen if you had from minus infinity to infinity? So you have a truly infinite interval. It goes all the way to the left towards negative infinity, all the way to the right towards positive infinity. Well, we can't fight two battles at once. We can't make two limits at the same time. So what we're going to do is another pretty smart idea. Let's break this up from negative infinity up to some arbitrary midpoint, and then from c on the rest of the way to infinity. This choice of c is completely up to us. If it doesn't matter, you can just pick 0 if you want. Negative infinity up to 0, and then from 0 on to infinity. So that doesn't matter though. You could pick 5, you could pick 10, you could pick -2. The point is that between the two of these, you are covering the entire interval, but you're just breaking it apart so that you only have to do one limit at a time. So anyways, this is how we tackle these improper integrals that are due to having an infinite interval. Now, the last thing we have to consider is what type of answers would we expect to get from these guys? Well, let's finish up our discussion with that. All right, so if you do one of these improper integrals that has an infinite interval or what have you, this is going to basically boil down to whether the limit exists or not, because we know that the definite integral will exist because we're only going from a to b, not a to infinity. So really it just boils down to this limit existing or not existing. So we say that this improper integral converges if that limit at the very end exists. And then we say that it diverges if the limit doesn't exist. And so if it converges, this could actually give you a finite amount of area even though the interval is infinite. I know that's pretty surprising, and we'll do some examples coming up shortly. But basically, in short, if this function decays quickly enough, you can accumulate area from a to infinity and get a finite amount of area. So even if you don't believe me right now, wait till we do some examples and I'll see if I can convince you that you actually can.